As we get further into our working with Haskell as a language, we're learning about more and more complex structures and type classes. In this video, I just kind of want to talk to you a little bit about the motivation for these things, where they come from, what they mean, and why we want them, why we care about them. Now, two of the big ones that we've introduced recently, and these are big things, they are things that are often the stumbling blocks for people learning Haskell, because they're very crucial to programming in the functional style in Haskell, but they're difficult concepts to get your head around. And these are functors, monads, those sorts of things. We've looked at functors and we've understood that they represent structures that can be mapped over. So for example, binary trees, they were examples of functors. Lists were as well, because we can map over them. And we also looked at some monads. We looked at maybe. You can see I've got a sort of bootleg version of maybe here. Maybe and either were monads, where you could build computation with them, and we saw how to do that. Now, these things, functors and monads, they can often be difficult to understand, because if you Google monad, you'll come up against something called category theory. Now, category theory is a type of maths I studied during my PhD, and it's interested in the mathematics of structure, or the structure of mathematics. And it's interested in composing and building structures from smaller ones. Now, you don't need to know the category theory behind these things to work with them. I'm just going to tell you a little bit about that, so you have a little bit more context and a little bit of understanding about why we care about things. So for example, functor, that's one of the core topics in category theory. So category theory, you understand categories, then you understand morphisms, functors, natural transformations, and then you appreciate universal properties. And then you have pretty much everything you need to go out into the world of category theory and study mathematics at its most abstract level. But functors are quite simple. They map between categories, or they can just be maps in a category. But what I want to get across to you today is that functors have to obey certain properties. So for example, if you have two objects and you map those objects using a functor and then apply a function in the other category, that has to be the same as mapping the function and then applying that to the mapped element. So and vice versa, you can apply it and then map it. It has to be the same as mapping it and then applying it. So when we define a functor, it should also obey some properties, which you don't really need to know, but that gives us a little bit more power, because we know that these things are coherent. We know that they obey laws and that computation is not broken by them. But really, a functor in this setting is just something that can be mapped over. If you have a bunch of functions that you want to apply across a big structure, a functor is what you want. Now, a monad is also a functor. Now, you might not know this. In category theory, it looks something like this: t, eta, and mu. These are the three things that you need to build functor. That t, or a monad, sorry, that t is a functor. Eta is the return function here, that's the thing that raises it, and the mu is the thing that allows you to do composition. That's kind of like the bind operation. It's not exactly the same, but it plays a role in that. So a monad is just a functor. Now, why do we care about these things? We care about these things because, as in category theory, as we do in functional programming, what we look for are repeating patterns, and then we try to build something that will abstract away all of that so that we just have one thing that we interact with, and that does all of the underlying work for us. For example, with functors, it's fmap. Fmap maps across structures for us, so that if I tell you something's a functor, you don't actually need to know how fmap is instantiated or anything like that. You might have an idea of it because you know what fmap looks like now, but really you can just say fmap f, whatever the structure is, and you're happy. And that's what we want from these. In the same way that a monad allows us to build effectful computation, which we'll see more and more of, and handle side effects, like for my maybe, like handling errors. Monads can also be other things. They can handle input-output for us. We'll see that later on in the course. They can also handle things like randomness. They can do a lot for us. And what they allow us to do is to stitch these effectful computations together without really having to worry about what happens in between. So they build computation for us. And that's why we're interested in monads. Now, you could think of these as similar to interfaces maybe in Java. It's not quite the same thing. It's hard to come up with a one-to-one comparison, but a couple would be interfaces or design patterns. You know, like things like the visitor design pattern. You see something that happens over and over again, you design something to deal with that. And that's what functors are. We map across a lot of structures, so therefore we define something to deal with that for us. Monads, we see effectful computation come up time and time again, we define something to do that for us. Now, one problem is that this definition that I have in front of me will not work. So if I save this and I reload, I'll get something that says no instance for applicative my_maybe. And that's because there is something that lies in between these two structures. So a functor is very general, a monad's quite restrictive. I should also say there are more restrictive structures than monads. There's more restrictive versions of monads. You could have like a bi-strong monad or a co-strong monad. You can have lots of different types of monads. And in the same way, the functor is not the most general things. There's stuff like monoids and other structures. We just take their names from maths. But in between the two is the applicative. Now this is a type of functor that Connor came up with, our very own Connor McBride at Strathclyde. Well, a lot of you will remember him from first year. Along with the traversable type class, he also has contributed the applicative type class to Haskell. And this is because he spotted a common pattern of computation which is not quite a monad, it's not quite a functor, it lies between the two, and is therefore much more prevalent than a monad, because as you restrict what your type is, it gets less and less common to come across it. So a monad is something that's quite special. A functor is something more general, and applicative is in between. But today I'm just going to show you how to instantiate this thing, because again I just want to give you more practice with looking at things, seeing what that must mean, and defining it off the bat. So let's have a look at the applicative type class. So if we have a look, you see it's a class functor f, and this means that f has to already be a functor. And in the same way, if I just quickly do this, if I look up here, you can see that a monad has to also be an applicative. So that's why we're getting that error there. So you can blame Connor for that one if you like. But you can see here, pure is something of type A to F. And if we look at the monad, it also has something like this. It has that A to M, the return. That's what's happening here, where you embed something in the monad. So an applicative has a similar thing that allows you to embed something in the applicative functor. This is where it has a bit more structure than just a normal functor. And you can see that if you want to define it, you'd have to define this pure thing, but that's easy. We know how to define that from our monad there. And then we have to define this thing here, or lift A2. Now, this looks more complicated. This looks quite simple, so I'm going to define this one instead. So let's say instance applicative my_maybe where. Now, pure is going to be very easy, so we're going to say that we have pure x is equal to my just x. So we just embed the value. Next, we want to define this odd thing here. So this is something that takes a function which is wrapped in the functor type, the applicative type, this f here. So you can see that this could be just, or it could be nothing. So that could be just a function, an element of the type, so that could be just x, and then applies it. So essentially what this is saying is, if you have a function that's wrapped in the applicative, then you should be able to apply that to an element of the applicative as well. That might be confusing, but let's have a look at this. So if I have just a function f, and I apply this in a similar way that I would bind to just a value x, this is going to be just, well actually these should all be my just, so I'll fix that in a second. To use the working with normal maybe. So this should be just fx. And this is where the applicative and the monad depart company, as it were. So here you can only say if we have a function wrapped in the type, then we can apply that to an element wrapped in the type. It doesn't, in the same way as bind would let you do, apply an element of the type to a function that maps from A to maybe A, or maybe B, sorry. So in the you can't just apply this applicative to elements like this as you could a monad. So it's not quite as powerful, but it is more generic to make up for that. Now, I have to define the nothing case. So there are two cases. There's the case where I have nothing on the left, and then I have just something on the right. And then the other case is where I have nothing on the right and just something on the left. And then there's the final case where I have nothing, nothing. However, if I don't have a function, then I don't really care about what the result of the function on that element would be. And if I don't have an element, I don't really care what the function would be either. So if I have anything that's not two just types, I could just say this is equal to my nothing. Like that. So all this allows me to do is allow me to apply maybe a function to maybe an element. And that's more generic than saying that I have to be able to get an element of the monad and a function that maps from a pure element to something else. And then chain the computation. So really, that's all we need to do today. I just want to give you this idea that in the same way that in Java you look at everything and you think, how can I take this to a class? How can I define the class? What functions does my class need? In functional programming, it's more an emphasis on what patterns have I spotted? How do I make this pattern generic? How can I define something that will handle this pattern for me in the future? In the same way that we've seen a lot of functions that are the sort of non-tail recursive recursion, which fold R gets rid of for us, like our original definition of factorial. We have fold R to get rid of that, so we have the foldable type class, and then we have the tail recursive version, fold L, that allows us to abstract away that pattern of recursion for us. I just want to give you this idea. Oh, also, you could think of binary trees as something that might make this a little bit more worthwhile. We've done this with a very simple type, but imagine that you have, for example, a binary tree full of student identities, and depending on the grade they get, you want to map something to their function or to their or details. So you could imagine having a binary tree full of functions, a binary tree full of values, and applying this applicative in some of those instances. Now that we have this as well, we could define Connor's other type class, the traversable type class. Might have a look at that. I should also say he did this in collaboration with Ross Patterson, I believe his name is. Those papers are out there. If you're interested in the topic, you can see where he got these or they got these ideas from. We might have a look at the traversable type class. That's quite a complicated one. I just kind of want to show you some of the stuff that functional programming offers and how it's quite uniquely different to the programming that you're much more used to. So yeah, that's everything for today. I just want you to take away there are increasingly more restrictive types, like functors, very generic, applicative is a little bit less generic, monad is much, much less generic. However, you get increasing power with these structures as you go along. And they just abstract away common patterns for us. That's really all it is. So that's everything for today. Of course, if you have any questions about this, please do let me know. Thanks.